Hello, everyone. And today we are going to talk about series. That's going to be our first kind of introduction to series. First, we are going to look back and recall what are the sequences. What is infinite sequence? Infinite sequence usually looks like this. 1, A2, A3, A4. Looks like ordered list of numbers. And infinite means that there are like infinitely many numbers here, right? If we add up these numbers, just place them as a sum in the same order, we are going to get something what we call infinite series. Usually, guys, instead of writing down sum like this, we are going to shorten it with sigma notation. And you probably have seen this sigma notation before. Instead of using the sum, uh, are going to use um, going to look like this. In the bottom, we are going to label the first term, the number of the first term. If you start with term number one, usually it's n equals 1. And if your series is infinite, you are going to put infinity over here, means that there is no ending term here. And you are just going to show general term under this sum, and that's going to be a short way to write down the series. And in some books, you even can see just sigma an without labeling the bottom and the top, because usually it starts with 1 and ends in infinity. So sometimes people are going to skip it. So guys, interestingly, that this infinite sum sometimes is going to have a limit or be equal to a certain number. Usually, guys, that's not going to be, you understand that if we take infinite amount of something, most likely it's not going to be some finite number. Like, if we start adding a sequence 1, 2, 3, 4, for example, imagine that we have a sequence 1, 2, 3, 4, and so on, natural numbers, right? The series which corresponds to it is going to look like this, n from 1 to infinity, right? This is general term. And what is going to be the sum of this? It's going to be equal to infinity. It's not going to be equal to any number, but sometimes sum of this infinite series is going to be a number. And in this case, guys, we are going to say that the series is converging. Uh, we are going to consider, of course, examples. But for right now, let's do more definitions. If we take not all terms of this sequence, but some terms, for example, if we consider first four terms of this sum, we can label it as S4, and this is going to be called a partial sum. I'm going to write it down like Sn, which is A1 and up to term n, partial sum of series. Partial sum means that you are not adding all infinitely many terms, but adding only 4 terms or only 15 terms, like whatever you prefer. You can make a sequence out of these partial sums. Let me write it down first, like to show how it looks. So first partial sum, it's the first term of a sequence, second partial sum is the second, the third, and the fourth, and so on. I'm going to actually write down how these partial sums are looking. Partial sum number one is just the first term. Partial sum number two is going to be the first term and the second term. Partial sum number three is going to be the first term and the second term and the third term, and so on, right? So, well, I'm going to write down partial sum number n, like over here, partial sum number n. Partial sum number n is going to be a1, and the final element is going to be an. Now, guys, definition. Definition. Uh, you see that we have a sequence, right? And sequence can have a sum. So we are going to say if the sequence of partial sums Sn is convergent. I'm going to put in parentheses, what does it mean? It means that there is a limit of this sequence when we bring n to infinity. And it equals to a certain number. Then we are going to say that the series let me move it a little bit over here, A1, AN is going to be convergent to that sum. Or we are going to say that the sum of series equals to this S. Well, why are we doing that, define the sum of series this way? Well, let's go back to the partial sum number n. What is going to happen if you bring this n to infinity? Well, if you bring n to infinity in this partial sum, you are just going to have all terms of this series, right? And that means that if at infinity the term of this sequence goes somewhere, that's where the sum goes, because the infinite term of this sequence is actually the sum of series. It looks a little bit funny, right? But usually this definition is very helpful when we are searching for the sum of series. Remember that we are interested in series for which this infinite sum is a number, right? I'm going to consider a couple of important examples, and I'm going to start with example which we call a telescoping sum, okay, to show you how this definition is going to work. And then we are going to think about geometric series. Okay, so let me first write down. I'm going to label it example number 1. I'm going to write down a series as like infinite series already with sigma notation, and it's going to look like this. And kind of have a question. Does it have a limit? Is it equal to something, or it's going to be equal to infinity? Well, when it's written shortly like this, sometimes it's kind of hard to understand how actually this series is looking. I'm going to write down the partial sum of this series. Partial sum. Partial sum of the series is going to look like this. Term number 1 is 1, and I'm just going to plug in 1 instead of n everywhere. 1 by 2. Term number 2, 1 over 2 by 3. Term number 4, 1 over 3 by 4. And term number n, the last term is going to be actually my general term, n plus 1. So this is n and terms together. So what we are going to do, guys, we will try to calculate this partial sum and then check what is going to be the limit. If when n goes to infinity, or we have infinitely many terms in this sum, we are going to have a number. We are going to say that the series, which is over here, is convergent and the limit is equal to a certain number. What I'm going to do, guys, I'm going to consider this fraction and kind of do some scratch work job over here. Please watch. I'm going to represent this fraction as a difference of two fractions. 1 over 2 minus 1 over 3. Let's see, like, is it true or not? If we bring it to common denominator, we're going to put 3 minus 2 and 2 multiplied by 3, which is going to be exactly 1 over 2 multiplied by 3. So we can represent this fraction like this. This fraction we can represent as 1 over n, or just like imagine that it's 1 over 2 and 1 over n plus 1. If you bring it to common denominator and kind of simplify it, you are going to get 1 over n plus 1. Let's see now how my sum is going to look if each of these fractions I'll represent as a difference of two fractions, like partial fractions actually, right? I'm going to do it. So my first difference is going to be 1 over 1 minus 1 over 2, right? Plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus lots of other terms. And the last term is going to be 1 over n minus 1 over n plus, right? Now, guys, I'm going to look at this expression and see that minus 1 over 2 is going to cancel 1 over 2, right? Go away. Minus 1 over 3 is going to cancel 1 over 3. Minus 1 over 4 is going to cancel something over here. I don't know. This one is going to be also canceled with something before. This one is not going to cancel because usually this one cancels with something after and we have nothing after. So what are we going to have left after we do this cancellation? 1 over 1 is going to stay because it's usually cancels with something before and there is nothing before. So we have 1 over 1 minus 1 over n plus 1. So nth partial sum as n equals to this expression, which is what? 1 over 1n plus 1. That's a nice expression, right? Can we figure out what is going to be the limit of Sn? Limit of Sn as n approaches infinity is going to be a limit of 1 minus 1 n plus 1 n approaches infinity. Limit of 1 is still going to be 1. Limit of this expression when n goes to infinity will go to 0, right? So actually my partial sum is going to go to 1 if n goes to infinity. But if I go back to my series, it's actually going to be the whole sum of series. So actually this series has a sum and the sum is equal to 1. You see? You can write it down. I'm going to just use green color. Circle this one and say it's 1 over here. So the sum of this series is 1. Very nice method of calculating sum of series is to use telescoping sum. You guys probably are going to see that it's kind of, if you look at this expression in general, it's kind of you decompose a fraction. Remember how we decompose fractions in integral? You have a fraction which consists out of two factors and you decompose it into two simpler fractions, right? Still probably remember how to do this, even if the fraction is more complicated. Yes, so we have an example where a series is convergent. It's not always going to be like this. I'm going to give you an example of when the series is divergent, but I cannot prove it yet. I'm going to prove it in the next section. Example number 2, again, this is just example to observe something. The series is called harmonic series. And harmonic series is going to look like the sum of a very nice series 1 over n. n goes from 1 to infinity. So it's actually 1 over 1 plus 1 over 2 plus 1 over 3 and so on. Well, no proof yet, but this one is divergent. And it's kind of, if you compare these two, difference is very minimal, right? We have 1 over n here and 1 over n over here, right? But there is additional factor n plus 1, and this one doesn't have it, and it's going to be divergent. Proof later. I'm going to show you why it's actually divergent. For right now, you just need to know that a series like this is called harmonic, and it's divergent. Do we have more examples of convergent series? Yes, we do have more examples of converging series, and I'm going to consider it right now. The very nice convergent series is going to be a sum of geometric sequence, or we also call them geometric series. So example number 3. I don't know. I think maybe I'm going to just give some general definition. Imagine that my sequence has a term which is looking like A, r to the power of n minus 1. Looks a little bit crazy, but I'm going to give you numerical examples. In this example, a is not equal to 0. Well, if a is equal to 0, makes no sense. All terms are zeros, right? And number n is 1 and natural numbers. And imagine that you take these terms and add them up from n equals 1 to infinity. And let's see if this going to have a certain sum. I'm going to write down the terms, how they look when n equals 1, 2. When n equals 1, I'm going to have 1 minus 1, 0, so I'm going to just have a. When n equals 2, it's 2 minus 1, 1, so I'm going to have a by r. And the next term is going to be a by r squared and a by r cubed and so on. Let me give you just literally example. It can be, imagine that a is equal to 1 and r equals to 1 over 2. Then you are going to have 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. So the sum of geometric series, just a very simple geometric series. But we want to do it in general because I want to prove formula for this. For telescoping sum, we don't have a general formula, but we have a method how to kind of calculate it by using partial decomposition, right? For geometric series, we are going to have a formula, but to obtain that formula, I'll need it in general. So guys, the idea or the question is it going to be a number or not? Are we going to have a number, the sum of the geometric series? Or maybe it's going to be a number for certain r's or a's and not a number for some other. Well, imagine that r, let's set up r not equal to 1. What is going to happen when r equals to 1? If r equals to 1, we are going to have what? Oh, a plus a plus a plus a plus a. Well, if we have infinitely many a's, no matter whether a is big or small, infinitely many numbers, same numbers, is going to bring you to infinity. That's like n a, the sum of n numbers, the result will go to infinity. So that's why we are going to exclude this like case r equals 1. So we are going to imagine that r is not equal to 1, okay? And maybe not equal to also negative 1. For negative 1, we are going to talk a little bit later. Let's consider partial sum. Partial sum Sm going to be ar squared. And the last element is going to be arn minus 1. Why? Because if you look at the general term is arn minus 1. And Sn shows the sum of n terms. If you have n terms here, this is term 1, term 2, term 3. You see that number of a term is 1 unit greater than the power of r. So number n is going to have the power n minus 1, right? That's Sn. What I'm going to do, guys, I'm going to modify this sum two different ways to actually find the limit later, okay? The first way, what I'm going to do, guys, I'm going to consider Sn plus 1. Imagine that I have one extra term here. Ar, and then arn minus 1, and the last term arn. Why? Well, because now last term is actually arn, right? So this is like the next partial sum. I'm going to see that the first terms are going to make Sn minus 1. So the sum which I'm kind of, Sn, sorry. Just if you compare Sn to the first four terms, first like 3 terms with dots, you're going to see it's the same, right? So what I'm going to do, I'm going to write down that. So this is Sn plus Arn. Correct? Just like I represent the Sn plus 1 like this. Well, actually, if you consider these terms, all terms besides the first one, you are going to see that each of them has r. And you can take this r outside of parentheses. So I'm going to write down the first term and then write down r. And what I have in parentheses, like if you take r outside. And then ar, because there are like r squared, I take 1, but I'm going to still have 1 left. And arn minus 1, like I take 1 r out of each term. if I look at what I have in parentheses, it's again Sn, because if you compare it to Sn, you see Sn, it's A, AR, and so that's Sn. So that's a second way to represent the very same sum through Sn. Because the sum Sn is equal to this and to this at the same time means that these two things are equal. If they're equal, I can put them into equation. Sn ARn equals A plus RSN. Well, I'll need to actually calculate Sn, my unknown, because usually if somebody gives me a sequence or a series, they are going to give me A and R. So how I'm going to do it? Usually in my class, like when I teach it face-to-face, I'm asking students to solve it. So you can put a stop over here and try to solve it yourself. I'm going to continue in like 5 seconds. So 1, 2, 3, 4, 5. And I'm going to start solving it. So what I'm going to do, I'm going to bring this term to the left side, and I'm going to write down Sn minus Rsn. And I'm going to bring this term to the right side, A minus ARn. Now, because I have Sn here and Sn here, I'm taking it outside of parentheses. And here, well, I'm not going to do anything like parentheses. I know that it's logical to take A outside of parentheses, but for my purposes, it's going to work better like this. Now, guys, the last step left is to divide by 1 minus r. So A minus ARn divided by 1 minus r. Wow. So I calculated partial sum. Like with telescoping sum, I calculated something for which, which is a shorter formula, not like infinitely many terms. Now I can search for a limit of this sum, because if limit exists, that's going to be the sum of my series. If limit does not exist, there's going to be no sum to my series. Let's see what are conditions to the limit to exist. You see, when n goes to infinity, only one term here is kind of going to change. All other terms are given and they're not going to change. So what happens to this term? If you recall my previous lecture, we had this term investigated. We know that it goes to 0 when r is less than 1, right? And it goes to infinity, or limit does not exist when r is greater than 1. It does not exist. I'm going to write it in short. Okay, does not exist. And when r is equal to 1, we are like, first, we're going to not consider 1 over here, just because we know that the sum is already going to be infinity. And when r is -1, we are going to have alternation A minus A minus A, and that's not going to give us any sum just because, like, well, we're going to talk about cases 1 separately, okay? Let's just cases when it equals to 1 later. Say later. I don't want you to mess up with everything else. So we know that 1 is greater than 1, it does not exist. When it's less than 1, the limit equals to 0. And when is equal to 1, we are going to separately consider these cases, okay? So, well, we don't need limit does not exist, because that is going to be crash all the whole limit, right? When it equals to 0, we are going to have the result A 1 minus r. So our sum of geometric series A r n minus 1 n from 1 to infinity is going to be equal A 1 minus r when r is less than 1. So this is a very super important formula, which is called the sum of geometric series. And you will need to memorize it same way like formulas for integrals. You know, antiderivative of 1 over square root of 1 minus x squared. Sum of G series. What G here? Geometric. We are going to have other series with different letters in front. Now, let's consider cases 1 and -1, because we already know that greater than 1, it's going to go either to infinity or kind of jump between positive and negative infinity if r is negative. But what is going to happen with r equals 1 and with r equals -1? Obviously, we cannot plug them into this formula just because it's going to kind of crush the formula. But r equals 1 is going to result into series looking like this. A, sum of A n from 1 to infinity, which is going to be a plus a plus a plus a r equals 1. Sorry, my class doesn't look very nice. It's a plus a. Or if we sum them up, we are going to have n a's, right? Partial sum. When we bring n to infinity, no matter how small is a, it will still go to infinity, the limit. Just because even a very small number multiplied by infinity, it's still infinity. Infinity overpowers, well, except 0, but even a small number, but a constant small number, you sum it up infinitely many times, it's still going to give you infinitely big numbers. Now, let's consider r equals -1. How my sum of series is going to look? It's going to look like this. A minus A plus A minus A plus A minus A. If you calculate partial sums, for example, that's S2. It's going to be equal to 0, right? S3 is going to be equal to A. 4 terms is going to be equal to 0 again, and so on. So guys, what are we going to have? A sequence of partial sums, S1, S2, S3, for which we need to find the limit, is going to look like this. A0, A0, A0. We see that this sequence is not concentrating around any number, because part of the sequence is going to concentrate around 0 and part of the sequence is going to concentrate around a. No limit. Limit does not exist. So actually this is only the case which is going to work when r is less than 1. This is called geometric series, and geometric series is one of very powerful series in a series theory. And we are going to use geometric series a lot. So just we'll need to memorize the formula. And together with telescoping sum, there are very, very few series for which you can know the formula exactly. Telescoping sum is one of them, and geometric series is the second one. But the amount of geometric series in real life is much, much greater than telescopic series. So I'm going to consider example of geometric series and just calculate the sum of series, because that's going to be usually a problem, like calculate the sum of series. So example number, let's say 2. So my series equals 5 minus 10 over 3 plus 20 over, sorry, something happened. Oh, sorry, guys. I accidentally stopped sharing. I want to re-record everything. So I pressed something on my screen again. 20 over 9 minus 40 over 27 and so on. So series is given like this. We'll need to figure out whether it has a limit or not, and is it possible to find the sum. First, we'll need to figure out like how the series is built. What we see that the first term here, a, is equal to 5. Is it actually geometric series? Geometric series is going to have a constant ratio between terms. So which means that term n plus 1 divided over term n is supposed to give you a ratio. Let's check if it's going to work for first two terms. So my term n plus 1 is minus 10 over 3. My term n is 5. And I'm going to figure out that my ratio is minus 2 over 3. Is it actually true? Are we getting this next term by multiplying the previous one by minus 2 over 3? Let's imagine 10 by minus 2 is going to be minus 20, but there is minus from the term. And 3 by 3 is 9. Yeah, looks like. Is it true over here? Yeah, multiply again by 2 and extra minus and by 3. Yes. So actually, my geometric series has a equals 5 and ratio r equals minus 2 over 3. Again, if you're sure that your series is geometric, you can always divide the next term over the previous, because how we build the terms of the series, AR square, you see that every next term is getting one extra R. So how to find R? Maybe you divide AR over 8, you get R. You see, if you're sure that you have geometric series. Now, what is the sum of this geometric series? First, is R satisfying our condition less than 1? Let's check. My r equals -2 over 3. Absolute value of -2 over 3 equals 2 over 3, which is less than 1. So the limit exists. The limit exists. Well, what is going to be the limit? According to the formula, the limit is going to be a over 1 minus r. Formula not complicated. Basically, all information from the series is here in the formula, right? A is 5, 1 minus, and r is -2 over 3. Sometimes people forget about the minus which comes with r or which comes with formula and kind of losing it. So we have 5 over 1 plus 2 over 3. If we bring it to common denominator, we have 5 over here 3 plus 2 over 3, and this 5 and this 5 cancels, and we have 3. So the sum of my series is equal to 3. That's going to be the limit of my, or sum of my series. It's not complicated, but you will need to know the formula. Okay. Okay. So I think we can kind of have more examples of telescoping sums in the homework, but for right now, let's move to kind of more examples when the series are convergent. Theorem. If the series converges some series, then limit of term n as n approaches infinity will go to 0. It does not tell us that when the term goes to 0, it's going to be convergent. But if you know that the series is convergent, term must go to 0. I want to show you the first why it works on examples and then prove the theorem. Maybe you will kind of have a better idea. I'll go to previous examples of the series. Let's look over here. So telescoping sum, if you look at the term, when n goes to infinity, you'll see it obviously will go to 0, right? Let's skip harmonic series for a second. Geometric series, the term, if r is less than 1, will go to 0 just because we know that when the base of the power is less than 1, then we have kind of decreasing function, decreasing exponential function. Telescoping harmonic series is divergent. So basically, we cannot apply this theorem to it. The term goes to 0, but the series is divergent. The theorem tells convergent series will have term going to 0. Divergent series, we don't know. For example, this divergent series has term not going to 0. But if you look at this series, which sum equals to infinity, term does not go to 0. For divergent series, we don't know. Term goes to 0 or doesn't go to 0. We are talking here in this theorem about convergent series. If the series is convergent, the term must go to 0. I'm going to show you how we kind of prove it. Remember that usually when we look for the sum of series, we are going to look for the limit of Sn partial sum, if it exists or no, if it equals to a number S or does not equal to a number S. I'm going to write down two partial sums. Partial sum S, which is like A1, an minus 1, an. This one is partial sum Sn minus 1. So we can write down that Sn equals Sn minus 1 plus an. Kind of, next partial sum is just addition of extra element. From this, we can write down that Sn minus Sn minus 1 equals an, the term. Now, if we take a limit of both sides, we don't know what is the limit of this, but because we know that this limit is equal to a number, because somebody tells that it's convergent, it's going to be a number as a limit of this one. And it's going to be the same number as a limit of this one, because these are actually terms of the same series. Of course, they will go to the same number eventually. Just this one is going to be one step behind, but it's still going to be around the same number. So what we are going to have here is going to be s minus s, which is going to give you what? Just 0. So limit of the term will go to 0. You'll probably tell me like how it's going to be helpful. We are going to get from this theorem so-called divergence test. In this chapter, we are going to have many different tests because cases of really finding the number for the sum of series are not going to be very like often. We are going to mostly have cases where we cannot find the sum of series, but at least it's going to be nice to know whether the series has this number, whether series is convergent or no. For telescopic sums and for geometric series, we can find actually like precise sum. For most of other series, we won't be able to find precise sums. So we are going to create different types of tests to figure out whether this sum actually exists. Does it make sense to calculate this sum, or maybe it equals to infinity and makes no sense? So this is going to be our first test, and I'm going to label it with number 1, divergence test. Divergence test sounds like this. If limit of an as n approaches infinity is not equal to 0, the series an is divergent. So why do we call it divergence test? Because this test only can specify if the certain series is divergent. So it's like a conclusion. If you apply the test, your final words are going to be divergent. You cannot apply the test and tell that something is convergent. It's called divergence test because the final word is divergent. Why it's going to be true? Well, imagine that the limit is not equal to 0, but it's convergent. Then we go to the theorem, and theorem tells, well, if it converges, that limit is equal to 0. You see, it's a direct contradiction to the theorem. So that's going to be divergence test. Divergence test sometimes is helpful to check if the series is convergent without really trying to calculate the sum. I'm going to show you one example. I don't know, example 3 maybe. Consider series, which is not easy to kind of imagine how we calculate the sum. So the general term is complicated expression, rational expression, and we are asking, is the limit going to exist? Well, I'm going to calculate limit of the term, limit of an, as n approaches infinity. So how can I calculate this limit? Sorry, I put sigma instead of limit. Limit n goes to infinity. How we can calculate this limit? Well, we can use limit laws we had. I'm going to divide by n squared, numerator and denominator. N squared here, n squared here. And I know that this one will go to 0 when n goes to infinity because it's 4 over infinity. So my limit is equal to 1 over 5. So guys, at infinity, my terms will be very close to 1 over 5, and we are going to have infinitely many of them. If you multiply 1 over 5 by infinity, you are going to have infinity. So because it's not equal to 0, we are going to say that the series is divergent by divergence test. So again, divergence test can only verify divergence. You cannot say something is convergent by divergence test. It's impossible. Okay. Maybe I'll consider one more example of use of divergence test. So this was a rational series. Let's consider one more. Example number 4. You guys already seen this series, right? This is harmonic series. Let's check the term. Limit of term n goes to infinity. We're going to have a limit of 1 over n goes to infinity. And yes, the term goes to zero. Does it mean that the series is convergent? Well, guys, remember, when the term goes to zero, we don't know nothing because the test actually only tells us something when the term does not go to zero. When term goes to zero, we don't know. Can be. So actually, when term goes to zero, it can be divergent or convergent. The test does not know this. But we know because I told you, and I'm going to prove it in the next section, that this one is divergent. But if you try our telescoping sums, you're going to see that the term goes to zero and it's convergent. So when term goes to zero, it does not mean convergence or divergence. But if it does not go to zero, it's 400% divergent. Because if you have non-zero terms and you have infinitely many of them, eventually you are going to get infinity. Even terms are very, very small. But if they are like a constant numbers, you are not going to get any sum of this series. Okay, well, I think that's all about the first introduction to series, and we are going to meet more tests and more information about series in the next section. See you next video.